time and in place today. Let's do some audio. Oh, where's this thing? Copy. You just want to share it out to the groups and then I will get started. Yeah. Okay. Hi, everyone. Just gonna give it a moment for everyone to join in, and then we're going to do this. In the meanwhile, I shall be getting ready. Oh, I need to do something like a pop-out. No, it should come. I should get a thing there. It's fine. Let's get ready. Let's get ready. Let's get ready. Let's get ready. Okay, cool. I think people are here. I think the people who are gonna come are coming today. So let's see. So status report. Let's start with yesterday. We had an issue yesterday because our headers couldn't go onto the computer that we wanted to use, which was the NRF 52840DK. This one. Okay, cool. So the problem was that I needed to solder those headers so that I can reach the microphone, and because I couldn't do that yesterday, I couldn't run the sample on this, and that became a problem because then I tried to run a different sample on a we're working on Wind River code. Then I tried to run a different sample on STM32F4. And then at that point, I realized that my OpenOCD was quite out of date, and that prevented us from running any sample that we wanted. So anyways, what I want us to do today is kind of just go through, let's see. I want us to go through this one. Gorgeous. We have DSP at the edge. DSP at the edge. So let's go through. Let us implement a simple audio application that does. I don't have enough RAM yet or enough memory to record audio. And I don't know that I want to record audio anyways, but I can do quite a bit of signal processing, detecting what is in the audio signal, and then doing something with that. And I can do a lot of that already, before we even get to recording and transmitting the audio and doing stuff with audio. You can do stuff with the signal in the first place. And basically what is going to happen today is we're going to have some sort of little softcore introduction to DSP, okay, which is digital signal processing. I think I've done a video on this before, but digital signal processing is where you take signals that happen in the continuous realm and then you put them in the digital realm or the discrete realm, and then you do something with them. Or rather, you use them for some sort of analysis or some sort of whatever. So the first thing we're going to do is actually go through the sample that I did yesterday and then run that sample. And then once we run this sample, we're going to basically integrate it into our actual application. And then once we have it in the actual application, we can now start doing maybe some sort of signal processing. Right now, let's just make sure the microphone works. And here's the code I wrote yesterday. So definitely, I was using a Hello World sample, and that's why it's got Wind River on it. I would love to work at Wind River or do something with Wind River. That would be cool. I have met them. They're very cool people. So anyways, let's go through this. So what we want to do is first of all define an I2S peripheral, and this is the peripheral we're going to be using today. This is the inter IC sound, interconnected system, integrated circuit sound. Basically, it uses it transfers sound between integrated circuits. Okay, it's the same as I squared C, but just for sound. So basically, this supports two-channel format, so you can do stereo audio. So you can do like a left and a right microphone, but we're not going to be doing that. We're doing just a mono audio because we want to do DSP on it and not actual audio stuff. And then we also have the format is it's 24 bits, but because I don't know that we have a uint 24. Anyways, we have 32 bits and we have 8 bits and 16 bits, but I don't think we have 24 bits. But anyways, it is a 24-bit aligned sample, and that will allow us to get packets of data as 32 bits, but inside the 32 bits, we will have, let's say if it's right aligned, all the data will be towards, what should we say, towards the right. So it's right aligned or left aligned. You define what you want. So that's what we're going to do. We're going to be using this peripheral to connect to a microphone. Let's look at the code. So here's the code. So we define some sane, let's say, frequencies. This is 16, and I think I want to use, rather than 16, I'm gonna go to, I think I would wanna use 44100. So that I get that frequency, okay? So sample frequency is 44100. 44100. 44100. I just used 16 yesterday so that I can test it out. 44100. And then config 64-bit 24-bit configuration. Okay, cool. We'll get to that. So we define a frequency, which is 44,100 kilohertz. And then we say our bit width is going to be 24 bits per sample. And then we're going to say our channels, we're going to have one channel. And then we're going to have a block size, or basically this is the amount of samples that we're going to. Block size is the amount of samples that we'll capture. So if each sample is 24 bits, block size means we'll capture 256 samples each 24 bits. And then block count, we'll have 2 blocks. So we have you can have as many as you can. These are arbitrary values, but what we basically mean is we have two blocks here, and we're going to do dual buffering with them. So we're going to process one while consuming the other, and so on and so forth. And then we have a timeout, which is basically how long the I2S peripheral should wait before it starts just recording for an available block. And then what we do is we define a K-mem slab. Mem slabs are this concept in Zephyr. Mem slab. So this is a way of dynamically, it's dynamic allocation, but it's dynamic allocation, but it is grabbed at compile time. I don't know if this makes any sense. So a memory slab is a kernel object that allows memory blocks to be dynamically allocated from a designated memory region. All memory blocks in a memory slab have a single fixed size, allowing them to be allocated and released efficiently, avoiding memory fragmentation. But since we define our memory slab at compile time, it's already pre-allocated, like it has. So there's no dynamic allocation that is going to happen. It's just we're going to use it dynamically and go and free it and so on and so forth. So basically that's what we're doing with the memory slab. We made a memory slab here, and the size of each block is the block size, and then it had the block how many counts it has. So imagine a stack of memories, something like this. So we have a slab. This whole thing is a slab, and then on this slab we have a stack. We are stacking just memory blocks in it, basically. And this block, the block size and the block count. So block size in our case is 256, and the count is 2. So we have 2 blocks, each 256 size. That's how this mem slab works. And then lower, we go into our main, and this was arbitrary sleeping so that I can get the logs rather than it running immediately. Because remember, for this device, we can't get the UART logs while we are flashing the device. So at some point it momentarily get lost. So what we do here, we slept for 20 seconds, we configure the device, and then after we configure the device, we then configure and flash the device, and then after 20 seconds it gives us enough time to jump back into the emulator window and connect to a UART pipe and get the logs out. So what do? We get and we'll do this again. We will do this again because this is an implementation in our main somewhere, and we're going to actually put it in a thread in our application. So don't worry about this. So we get a device, and then we get a struct for configuring the device, and then we define a memory block or a pointer to a memory block. Remember those blocks that we defined up there? So this pointer is to the individual memory block, and then we define a size t that we're going to use later, and then we get a ret that we're going to, as we're always using in Zephyr for error checking, or rather for branching in our functions. We configure the word size, which is the bit length. We say how many channels we want. We want just one channel. And then we configure the format to get I squared S later. And because we're on the microcontroller side, we're on this side at the moment. So there's 2 sides to this. There's this microphone size. This is the control part, and then this is the controller part. So because we're on this part, we set the clock to master, and then we choose a sample frequency, and then we tell this this peripheral, this is the memory slab that I want you to be pushing data into. So what happens is via DMA, I2S is collecting data out, and then as it's collecting data out, whenever it gets to the block size that we want, it gets to 256 samples. It will then copy using DMA into the slab, and then we can use that. We can use that slab or blocks in that slab as we wish, and then we say how many the size of the blocks, and then we use a timeout. We can say wait. This timeout is basically how long to wait until you can use it. Okay, cool. And then once we do that, we configure and check whether it was configured, and then we check if the device is ready to make sure that we have a device. And then later along the line, we can trigger a start, and then inside after it has started, we can consume the data from the slab. So here you can see for each memory block we print around I think something like 10 or something, 10 samples or something. What is I plus, I less than block count 2. Oh, no, yeah. So for each block, we just print 10 samples just to see that it works, and then we trigger the stop. Basically, that's it. That's all the code that's in here. Let's build this code and run it and see what happens. Activate. Cool. And then Control R. West build. Yeah, let's build it like that. And then Control Shift T. I'll open a terminal there for when we want to run the login. Ooh. I know what's happening here. Let's just set the timeout that we were doing. I was doing some experimentations. Timeout. No. Wow. I was doing some experimentation and I wanted to see if that would last. Let's build it. Yes, Sean, you're here first. Welcome. As it's building. Amazing. Okay, if you guys have any questions now while it's building, it's a good time to ask them, and I'll see if I can answer anything. You can ask anything, I guess. It's building. It's gonna build a bit. When you're confident of your code and it's building quite a lot, you don't have to use the always flag because you've changed something small, and you can let Zephyr determine by itself. And then I think we want Control R --HW. HW. Yeah. Let's do that. Let's do this. Let's use HW here, and then let's package that application we built into some sort of audio zip. Okay, and I'm gonna mount DFU. Okay, let's do audio zip. So I first have to make this go into bootloader mode, and that means pressing that button. You should see a red LED. Yeah, it's in bootloader mode. There's a red LED somewhere there. Okay, cool. So now it's in bootloader mode, and if I run this function, it's gonna flash that the code into that. Okay, cool. Let's flash it. Yes. So this is the part I was saying. When it's flashing like this, we can't be running TTY. Let's get a screen. Let's run a TTY. It's gonna be off, and then at some point it will boot up after 20 seconds. I should reduce the boot up period. Okay. If anyone has any questions, please do ask. Yeah. Cool. Look at what happened. So we got audio samples. It's zeros for now, but we got audio samples for all the. I think it probably is zeros because I'm not doing the sign correctly. But what this means is our code ran all the way to here. So the configuration was a success. The device was ready, and then after that we did do the trigger, and then we counted all of this, and then look, device setup works. We're logging that every 2 seconds. Let's see. Are we logging that every 2 seconds? Yes. So that means we have all the things. And basically we went through here. We got all of this. It did read because it returned successful, and we got all the data back. So now let's do this. Rolling. Okay. So let's go to our application, and then we can do the implementation there. So now we can apply the code. Applications. Zephyr custom. Yeah, okay, cool. I don't know why I keep naming Zephyr applications with Zephyr prefix in the Zephyr thing. Oh, it's because of GitHub. And Vim I. And then the first thing I want to do here is go back. Just trust me. Go back into Zephyr itself. Go into the samples. Go into Hello World. Go into source, this, and then space E. Control A. Hey, space A. Control E. Okay. So the first thing we need to do is prepare our device tree. Remember? And the device tree is how we assign a driver to a device. So the thing we would do is we just get this. I'll explain all of this. So let's copy this over and then let's take it into our application. This is in Zephyr. I don't want to be in Zephyr. I want to be here, and then I want to go into applications, and I want to go to custom BLE service application, and then in here, let's go into our app.overlay. App.overlay. So in app.overlay, we did this. This setting we did previously was to enable the temperature sensor on the temperature sensor on the NRF 52840, and that's the sensor that we're reading. Okay, so now let's add the code that we copied from the other place, SP, and basically let's explain this. So the NRF, let me explain this. NRF 52840. Yeah. So the NRF hardware, go to hardware, and then go to, while that's opening, do we have any questions? No. If you have any questions, please, I encourage you to ask. Let's go into the hardware description, and let's go into the hardware drawings, and then I shall relate this to you guys. So this NRF dongle looks like this. Okay. So here's a dongle. And let me open YouTube just to make sure I am showing this right. So this NRF dongle looks like this. And basically what we are doing is we are connecting these pins out. So let's look at it. This pin out, this is a VDD out, this is a ground out, this is a 0.31, this is a 0.29, and this is 0.02. Those are ports. The 0 is the port and the 29 is the port number of the thing itself. So look, so what we're doing is we're connecting those those wires out to the mic. And the way you do this is you do this in device tree in Zephyr. I don't know if I've done device trees, but I should maybe cover device trees. So you have that. Okay, cool. The way it's connected right now, I'll put it close to the screen. The way it's connected right now is that the VDD is connected to the VDD of the sensor, and then the ground is connected to the ground of the sensor, and then the 31 is connected to the word select of the sensor, and the 29 is connected to the bit clock, and the 02 is connected to the data pin. Let's go and relate that into what we've done. So let's look at the device tree that we're setting up right now. We're doing some pin control here, which means we are changing how the pins are defined or rather the functions of the pin in the application. So we're doing some pin control here. And then here, I have a feeling I can I do this in overlays? Will it work? Okay. Assign, okay. Let's see. All right, let's comment here. And this code will be uploaded later so that anyone can try it. Assign pins to I squared S. So we can use a mic. Okay. As you can see, like I said, 29 is connected to the master clock, which is the bit clock. All right. And then 31 is connected to the word select, which is the one that it's a long one in I2S that selects the thing. And then SD in, which is into the microcontroller, we have 02. And these pins are somewhere here, I2S. So the way I2S, there should be a block diagram somewhere here. So you see we have STD out, if you're using it, we're not using it. And then we have STD in, that's the one, SD in, that's the one we're using. And then we have a SCK, that's a bit clock. And then we have a word select. and those they're basically it's one of them is for setting the frame size, the other one is for just the normal clock for the communication, and the other one is for the actual data that is coming in. Okay, we can cover this later in an actual device driver implementation, but we'll see. Right now, let's make the application work. Okay, cool. So we've done that. We've assigned pins to the microcontroller, and then here, let's activate the I2S peripheral by setting status to OK. Okay, and then before I jump somewhere else, in case you want to learn this stuff, Zephyr device tree. So if you want to learn this stuff, the stuff I just talked about, look at this link, which is going to be in the chat. Let us put this link in the chat. Okay, cool. In case you want to learn this stuff and you want to follow along with the device tree, there's a device tree guide in the chat, and probably I can also put it in the blog somewhere. Yeah, let's put it in the blog or rather in the notes. And then let's add a line here, and then under the line, let's say references, and then in here let's say Zephyr device tree, and then in here we go and then we can also add do we need I2S? No, I think that's fine. So cool, let's put that there. Okay, cool. So we've defined, what have we done? We've defined an application, we've defined pin control, we've assigned some pins to something, and then we've also we've assigned some pins to something, and then we've activated an application. This is actually a good test point. Let's go into our application. Yeah, so this is not where I want it to be. So cd project applications and then Zephyr custom. Let's go into that. Let's build this and see if, first of all, let's look at the ls build. Is there a build? Yeah, cut build Zephyr .config, yeah, and then in here I want to grab I2S. Yeah, cool. I2S is not set. So what does this mean? We found something. This also means we have to set, we have to enable the I2S configuration. This is good. So then in here we're going to have a project config, and then in here in the project config, this is how you activate and deactivate. This is kconfig. I will also share a link on this. So audio configs. So here let's activate the config I2S equals yes. Let me just segue a bit and show you guys where to get the information for that, so that you don't have to really suffer when looking for this. When I did that config, I messed with something called the Zephyr kconfig. Yeah, Zephyr configuration system. So the Zephyr kernel and subsystems can be configured at build time. See. The Zephyr kernel and subsystems can be configured at build time to adapt them for specific application and platform needs. Configuration is handled through kconfig, which is the same configuration system used by the Linux kernel. The goal is to support configuration without having to change any source code. This is This is so cool because when you're doing bare metal applications, like when you're doing something like GitHub, Zach, let's do, Gaiocho, UC DSP. So when you're doing a normal application, what you have to do is you have to make drivers, and then inside your drivers, let's look at this, say, accelerometer driver from ST. Inside your driver, you basically write the code to speak to that for each application. Do you see? So this is basically in a drivers folder. This is not even the source folder of our application. If you look at it, our actual source folder is here, and this is our actual application. And then in the application, we have all these drivers that we pull in. And then once we pull these drivers in, we can do stuff with those drivers. And then the thing that Zephyr allows you to do is Zephyr allows you to build all these drivers. You're still doing bare metal development. You're still doing the bare metal development. However, you're basically you're dividing your application into layers. You're like, this is the hardware layer, what we did with pen control. This is the drivers layer, which is Zephyr's drivers thing. Zephyr has drivers in it. And then in the drivers, you define drivers for every possible thing that you want. We were looking at a driver application in a previous thing. And then you can now use, I'll show you. Pull. Yeah. So here's a pull request that I'm adding to Zephyr. And in this pull request, if we look at the files changed, this is just a driver application that's coming in. What we have is a kconfig here. And the kconfig allows us to say that this thing has been set up. Okay? So by just setting this kconfig in your application, you are allowing your application to use this driver. So effectively, what we just did by doing this is we are allowing our application to use the existing I2S driver, and this I2S driver is somewhere here. Let's look at it. Just bear with me. It has an I2S driver, and it is covered. Sorry, it's covered somewhere in here. It's Nordic I2S. Basically, it's there, but I don't want to jump into code because we'll get confused, and jump into this and we'll get confused, and then I'll lose my train of thought. But basically, what we did by doing this is we activated a driver that previously was not activated, and you can tell it was previously not activated because when we check config here, it's not set. So cool. Let's look at this, and then if we check, if we do a grep on let's look into Zephyr DTS. Zephyr.dts, and then we do I2S0, and then we do A10. Brav grep. Okay, cool. So look at what is happening here. Basically, what I want you to notice is the status is disabled. What does that mean? That peripheral is not enabled. We're not using that peripheral currently. Okay, so let's clear this. Let's do a git diff so we understand what code we have changed. In our app.overlay, which is how we define, if you look at the device tree link that I said, find device tree overlays, you will see that app overlays is what you do. So there's the board, and then there's the application. There's the board, and then there's the application. So you can define a board without defining the application. And then you can apply an overlay on the board that defines what this application is. So we just added an overlay that added I2S, and we added a kconfig to activate that driver. Here it is. That's all we did. Okay, cool. So let's build this and see what changes. West build. That's fine. Let's build it there. Let us build it and see. Well, because this build takes long. This is our actual application build. This is a longer build than the other one. I'll go check for questions. Any questions? Right on. Anyone with any questions? Anyone with any questions? I'll check what's up. Let's see. I hope it does build. Okay, cool. So anyone with any questions, please do ask right now because it's building and I can't answer them. Let's build that and see what changes, if anything changes. Okay. That's slow. Okay, that's building. It's building. It's building. I hope I can get to doing the DSP part today. I probably will if I push along hard enough. Oh, amazing, it built. So let's now look at the two things that we looked at before. Okay, let's do that. So the first thing we looked at before is we checked config for I2S. Boom! Wow, look at how many things have changed. So, what does this mean? It means config device tree has Nordic NRF I2S enabled. Yes. Config NRF X I2S. Yes. Config NRF X I2S 0. Yes. Has hardware NRF. Yes. So all of these are settings that have come alive the moment we set the config I2S. So we've activated this driver. Remember, kconfig again. The Zephyr kconfig system allows you to activate and deactivate drivers without changing source code. Okay, cool. Technically change source code, but you don't have to. Your machine will do it for you. Okay, let's look into our device tree. The Zephyr DTS, and then in here let's grab I2S 0 and then say A. Wow, that's even a lot more than we expected. What I want you to notice is I2S 0 is set up, and then the thing I really want you to notice is now the status has been set up okay. And then actually if you're keen enough, you will notice that it says this comes from this file, the Nordic ARM Nordic. We can actually go to that file. Zephyr DTS ARM Nordic DTSI. Zephyr. Let's quickly jump into that source code. I would close that because I want to use it later. Zephyr. Let's jump into that so that we can see. So we go into DTS ARM Nordic DTSI. DTS ARM Nordic NRF 5280 DTSI 52840 DTSI 52840 DTSI. Here, you. Which line? It tells us which line. 489. Line 489. Let's go line 489. Can probably use Vim key bindings here. 489, line 489, line 489, line 489. Ooh, amazing, look. So this has been added from here. Do you see? The device tree has been added from here. So this device tree here defines our board. Let's see if the temp is in here. Temp. Yeah, you see this, here you go. Temp again. This defines the temperature thing. And what you might notice is, so this comes from there, but then look at here, pin control O. This comes from applications app.overlay. Cool, app.overlay. App.overlay. Look, app.overlay here. We set the pin controls here. Let's look at here. It comes from in applications, Zephyr custom application app. Zephyr custom BLI app.overlay line number 21. Do you see what happened? Okay, and this one as well comes from line number 20. So basically, we're looking at this one, line number 20, line number 21. Look at the line numbers. Okay, cool. Our build system tells us exactly where this code is coming from to activate this thing. Perfect. That's done. So we have activated I2S and we're using it. So now let's go into our main and see how we should do this. So here in our main, the thing that I see our thing is doing is we are almost using this is our complete main. So we're doing a thing that is we are doing a thing that is service oriented. We're making some service and then we run it. So the thing I want to do is probably be able to run an audio thread here. So I want to do something like k thread define audio thread ID some size. You can even go with the same one, thread stack size, and then in here we want to do something like audio sense thread, and then we want to do null, and then null, and then null, and then we'll make this the most important one, and then we'll do 0, and then we'll do 0. You know, something like that. I want to do something like that, but this will crash right now because the audio sense thread, audio sense is not defined. This needs to be some function defined somewhere, because if we go so if we go here and say this is actually in BLE service, BLE read thread. So if I go somewhere like PV and then here, and then you'll see there is actually a function here, BLE read thread. So what does that mean? We need to make let's make an audio service, and then we import it into main, and then we can do that. So cool. So in here we need to, I probably should make this later. I will make this an actual CMake application where all the files will disappear and all the headers will disappear, and then suddenly we are like in some sort of really clean land. So audio service.h, yeah. Let's go into temperature.h. Yeah, I wanna take this one. It's way simpler. Why? Really? I could have just gone here. So let's do audio service.h. Let's change this into audio service.h, and then define this audio service h, and then I can remove audio service init. Let's do audio service init. Let's make an audio service init, and then double fetch temp. I don't need the double fetch temp. I don't need to return anything, yeah. And then I think I need to do something like and then in main, what did we do? Audio sense thread. Audio sense thread. Audio sense thread. Take some 3 arguments that are nothing. This in theory should make our app build. Might not build. Because this thing is not defined. This function itself is not defined, so it's not gonna run. So let's not even try. It's okay. Now here's where I want to space A, Control E. Okay, let's go back. Now let's go back and forth. We need the kernel and we need the kernel, which we already have from main by the time we call this. So we don't really need it. We need the drivers I squared S. We can actually just copy this if you want. And then where do I want to do that? In some global somewhere. J. And then let's do Y. And then in here, let's come and do this. Yeah, let's do that. And then what do we want to do? We want to make an implementation of this. Does anyone know how to set autosave in Vim? Brian probably knows. He can tell me. Audio service.c. Okay, this let me save here, and then let me check questions on YouTube if anyone has any questions. No questions so far. Okay, cool. Let's go. Questions on WhatsApp? None so far. Let's do the thing then. Control E. Let's jump into here, and then we want to just let's be let's audio service, let's see, and then SP. So as soon as we run this, we put this in here, and then in here we will do in hash include, and then in here we'll do audio service. Okay, there's that. That has been set up. All of those things have been set up. So we have that, and then we now want to define an audio init. And then let's go here. We want to define this too. We'll get to that one as well. So let's wire this PV, and then in here, I don't even need to do that. I can actually Control H, Control K. Anyways, I can walk through the files quite easily if I remembered. Yeah, we are in here. We're gonna be in here. So what I want to do is, I'm not gonna do all those sleeps things. I'm not gonna do the hello board. I want to set up my audio peripheral, all of it. And if it doesn't work, I want it to explode. Y. And then we can go into the audio service, and then in audio sense init, in here we can do something like boom, boom, boom. Yeah, there's something I'm missing, some definitions. This one's I'll see. Why? I will see. So I'm missing those definitions. So let's put them in. And then what I want to do is, I think I want to put this guy. Generally, this guy, I want him to exist in here. And then void audio sense, and then in here we want to do and here we want to do something like log 1 I sense not implemented, and again, and then that, and then that, and then that, and then that, and then boop, and then j. I don't know if this will work. This does need Zephyr logging, PV, and then if I go into the BLE, something like the temperature service, I want to get this part. Log module, y, SP, and then in here I want to include, before you I want to include, let's include the Zephyr logger module, include something like Zephyr logging log.h, something like that. Anyways, let's look at that. Let's look at here. Logging.h, yeah, print k, log module.register. Let's see. Log module.register, all of that stuff. Okay, cool. We sort of have some sort of thing that should build. Let's look at our git diff. Git add prj git add up over there, git commit git check out dash b br add audio sensing git status rm-rf pull dot some defect of something, clear git commit dash m audio sense, add device tree overlay and kconfig. Perfect. Okay, and then we need to git diff. What have we diffed? Is that all? Ooh. I see what you want. So we have a diff. We've added this, but git status. Let's git add src main. Git add src audio all. Git diff dash staged. Let's look at what we added, just to make sure we are sane, and then we'll try and build it. So we added an audio service.c, and it includes some logger, and it defines memslab, and then it's using all of this stuff from the header, and then in here it checks if the device is ready. So this is audio service init, and then if that is ready, it will and then there's a thread function, and then there's an if define, if def, that is working there. Okay, cool. So I think what we need to do is, before we even commit that, let's try and build that. But before we build that, let's try and make it so that main actually tries to run everything. So let's add here something. So it goes like and then we'll say audio service init, and then we'll do something like audio and then I think this is GG, and then we did insert, we did bring it in. Okay, so let's build this and see if that's a lot of code changing. So let's build this and see what happens. West build. I can actually just go up again. Don't worry, don't fret. Let's build it. So while it's building, to everyone on the chat, or rather the people online, can you give me a thumbs up if you can see this? And let me know if you have a question, or if you want, even if you have a question that says, what the heck are you doing? That's fine, because then we'll figure it out. This is not good. This is not good. Service C, 31. Let's go. There's sheep outside my window. Service C. I know what's happening. This should not return. This should not return. So this should be like, okay. So let's do a log error. Okay. This should either be breaks or not. Anyways, let's do a log error. Should we break the app? Yeah. We should break the app, so what if I do that? And what was the issue? Yeah, that's fine, that's all fine. There's no error in there. What's the actual error? Log constants of module. Thank you. Audio module. Okay, cool. Let's build up. Let's see. Any questions? Any questions? Does anyone have any questions? So one thing, which I think we'll use later. Yeah. That. We're not even gonna use this in it. So I'm gonna do this and put it in some global scope of some sort. P. And then in here I'm just gonna so we should have some sort of clean build. Let's see, 259. That means we've added code. Okay, let's see how that goes. Let's see how that goes. Let's see how that. Oh, it built. It built. Oh wow. What if we run it? What if we actually try and start the thread? Control R, hardware. Yeah. Control R, DFU. Let me do the thing. Okay, it's ready to be flashed. You can see here that it's ready to be flashed here. It's the screen is. It's fine. And I also have no sort of. I think it's gonna explode. The reason being, it's gonna be the. Yeah, sense not implemented. See here, sense not implemented. That's perfect. That's perfect. Yeah, amazing. So we are running our audio sensor, and because we are running our audio sensor here, that's fine. It works. Okay, so let's implement some sort of fixed sensing, because we want to just get the sensor working. Okay, just get the sensor working, and then from there on we can explore how it can become a DSP thing. Just be able to trigger a sense, and then we'll go from there. Okay, cool. So that is working. Let's now in here. Let's do this. Let's look at the temperature service just one more time so that I can just look at the initializer is fine. I don't need that reader for now. I just want to see what's happening in here. Yeah, and then we sleep 2 seconds and then we do it again, and then sleep 2 seconds and we do it again. Okay, cool. Perfect. Let's go here. So we basically want to run this. I don't really need intret, but I will use intret again. Vim. Yeah, let's just take all of this. Why? And then let's go to our audio service, and then let us do this. Then let's do that. And in here we can go in here. We can say something like while 1, and then do that, and do this, and then in here we'll come in and we'll SP. I will run Clang format on this later, and then in here, before we get to this, let's do an int ret. I'm actually gonna do that now. Let's see, Control R, Clang format, and I'm in here, I'm in BLE service, so I can go source, audio. Yeah, sure, both of them. Cool. Yeah, it's going to have been. Yeah, so here it goes. It's been formatted. Let's look at it quickly. Let's go through here. So this can't return, number 1. And then once it ends, we will sleep. 2 seconds. Let's go here and see. I want to see the temperature. I want to do this. Yeah. Let's just get that. Especially on stream, it's way easier to copy and paste code every time rather than type it, because this. Wait 2 seconds, then sense again. Okay, and this was static before, because basically before what I was doing was I was just grabbing the data. Remember? Let's again. Let's just let us think about it. So before here, I was doing. Oh my word! Before here, I was doing this because this is running in our main loop, and I wanted to test this. I was just recording once and then stopping. But that means our slab was full. You see, yeah, you can come up here if you want. Our slab was full, and then once our slab was full, I would just, I would stop. And do it. But now there's a thing. We need to. Let me go here, and then let's do kmem slab release, something like a free. So memory slabs, yeah. Don't type, please. Yeah. So we see we use a memory block pointed at by block pointer, and then we can free. You see, basically, we can basically free it after we use it. Okay, and what that means is once we've used it, and because the thread is going to be running periodically. Once we've used it, we can clean it out of the system. And then the next 2 seconds when it comes by, it will be available to use again, and then we can use it again. So let's just go through this and make this work. First of all, okay, this is in the wrong place. So let's go here. All of these are logs, Cool. So first of all, let's look at this. We trigger the thing to go to sense, and if it fails sensing, we want it to tell us, and we probably want it to return. So let's do so let's hear log error failed to start thing. Okay, cool. And then for that, into block count, read each thing into the mem block. So we read into that mem block, and then we still need to free that mem block after we've done it. When do we free that mem block? You see here, let's remove this. This actually doesn't need to be here because we will be doing, everything will be in its own line. So, this is a mem block at a time. In this function, in this loop, we're touching one mem block at a time. So if we use this and we free it, the next time we come to use it, it'll be okay. Okay, so in here, mem slab free, and then in here we need to do something like, do we need to refer to our own slab, to our slab, and mem slab, free mem slab, and then in the mem slab we need to also the mem block. Okay, that's it. That should work. Okay, cool. And then in here we want to print, in here we want to log one, so we can get the log. And then in here we want to log error, but this is a special case. We kind of continue. let's put a to do here. Should we continue if we fail to read? Yeah, let's do that. Log 1, log error, and then let's just go through all of this, see what happens. And then here I want to say I2S stopped, so I will log 1 here so that we can see it. Log 1 so I can see it, and then okay, and I think we can build. Basically, let's see if we can build. Again, back. Does anyone have any questions? Does anyone have any questions as that is building? I know what's wrong with that. I know what's wrong there. Kind of want to use it everywhere. I know what's wrong with that. So, here's the issue. You see this device that we're using here? We don't have somewhere it's defined. If we go back to our main, this is here. See, this is all here. Construct device, da 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 da. I wonder if I can do construct device. And then you need to do that. Right. Let's see here. Do I do here something with the device? Yeah. So can I just go outside of here? Can I go construct device I2S? Device, and then I'll depend on that being called, and then here I can go something like that. It's already a pointer. I need to find a way to get CMake to make my stuff work. I don't understand what I needed to do to make my CMake work. Okay, yeah, it is. Let's see. Yeah, basically what I'm doing here is the same thing I am doing in temp. I have a device at the top. I do have this device here, temp sensor, and then I set it as I use it in the functions. That should almost work, almost guaranteed that just works. Almost guaranteed was not guaranteed. So here, what do I want to do? Static construct device. Yeah, and that's there. Okay, cool. And then construct device. Wait. Static construct device. Yeah, and then temp sensor is set to that. And then when again do I use the temp sensor? I must use the temp sensor. Yeah, I just gave it there. I just use it there. And then why are you complaining? No. Let's look at the temperature again. Static construct device. Is that it? Is that really it that we want? Is that all that we need? Value service routine. Static construct. This is my C coming into question. Yeah. If anyone has any questions while we're building, always I'm offer for questions while we're building. That's not good. Okay, cool. I need to open this both at the same time. Let's go into GitHub and open this in a different way here. Let's look at the temperature.c and see what we're doing, right? Drivers, sensors, drivers, blah 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 blah. Okay, cool. Static const drive. Does that? Yeah, that's fine. Okay. Static construct device. Device dt get any. Why can't I use? No, so static construct device, that. And then I just get it in there and I can use it. Why can't I use it now? Is it because I don't have device.h? I don't need device.h. I don't need device.h. I2S device is defined but not used. Something really tiny is wrong. Static construct device, I2S device, yes. It's the exact same thing here. Static construct device, boom. And then in here we do that. Just static construct device, static construct device, static construct device, the device itself, the device itself. This is a pointer to the device. We're declaring a pointer to the device. And then in here, we go and get the device dt get that guy. But that's get node label. No, I don't understand. This is going to be fast error. Where is the fast error? In number 15 here. No, I did not mean to use that. Unless you want me to get device.h. Zephyr device.h. Can we try just Zephyr device.h and see if that actually fixes it? It is there. It's already there. Temperature H. Yeah, it's already there. Main. I don't need a device in here. I don't do anything in here. So there's something I'm doing wrong in here that is silly in some sort of weird way. device dt get any. Let's look at Zephyr device dt get any. Device dt get any. Yeah, takes a compat. Where did we say that thing is coming from? It was in NRF. Control A as Control A DTS. DTS ARM. Yeah, this one. We can use that and see if that works. Perhaps. F I2S 0. No, this wasn't the one we wanted. Yes, Nordic 5284 52840, just a normal and DTSI, just a normal DTSI, 52840 DTSI, and then in here S, and then in here I want to do Nordic NRF this. Copy. So let's use a compat. So let's do device dt get any, and then I think we are using a compat. Let's look at our card get any, and then we're using a compat, and then that is and then let's go into that, and then let's do that, and then let's do this is this, and then this is this. The problem isn't this. The problem is this. But this is here. I'm the biggest fool. Check, guys. Here's the issue. Typo. Okay, let's see again. Oh my god. Development is a debacle. I've been streaming for an hour now. I'm probably gonna go for another 20-40 minutes, between 20 and 40 minutes, because once this works, we basically have the introduction to the DSP thing, and I think we can leave that as a PR and push it up. I think so. I think as long as it works and we get logs, we're good. It built. Let us compile it and run it. So let's package it. Okay, cool. I'm gonna put my device into bootloader mode. It is in bootloader mode now. Let us packet into the device. Boom. And then we will see what happens. Okay, cool. Go here and let's run our screen and see what we see. Oh wow, do you see what's happening? So every 2 seconds we're getting all this, every 2 seconds we get this registrations. Unless those are wrong. And I don't know how many seconds we set in between, but we are getting audio packets. You know what I wish? I wish this thing had something wrong. Something is wrong. So yeah. Samples J failed. K sleep. K seconds. 2. Trigger stop. Audio sense. Trigger start. Da 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 da. Well, how come we're only getting them once? Once. I don't see why we're not getting audio packets every 2 seconds. It doesn't make sense that we are not. It doesn't make sense that we are not getting. They should be constant. They should be every other 2 seconds. It should show us something. But it's not doing that. For some reason, let's go through. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. So all the variables are there. But for some reason, our thread only runs once, and then it doesn't run again. So let's look at our BLE audio service. And in here, let's determine we trigger start. We do all of this stuff, and then we do all of that stuff, and then we do that stuff, and then here we do that. I mean, somewhere we're messing up. We do get data the first time, but somewhere we're messing up because we're only logging once. Yeah, audio module failed to start. It stopped. You see? It stopped. And then it doesn't start again. It fails to start. Basically, what we can't do in order to get that, if we want to get that, error, so let's do main, and then in here let's do something like remove that, and then in that way we can just run it again. So the issue seems to be our thing fails. I think it becomes where we call the trigger start. So while one, two. Let's see. What if I told you? Let me see. This while as well. No, I want to see. So this one. Yeah, but that one. Yeah, that's there. And what the end there. And then this just goes all the way out. I kind of know what the issue is, but I don't know how to fix it. So the problem that's happening now is, let me do this so we can see. So the problem that is happening now is that here. Something is wrong. Something is wrong in the way we do this. Let's do this and let's see this. Let's do that. Let's see if that fixes it. Maybe I'm actually using the wrong. I'm using the API wrong. In some weird way, I am doing something wrong by freeing the memory slab or the memory block. So that way it fails. I wonder if I have to do allocate as well. Because then that would fix it. Do I have to do allocate so that I can so that I can make it work again? Let me see. Okay, let's package that. Okay. And then let's push that into the device. And then in here, wait until it's done. And then in here we can do some yeah, you see, our audio module captures a lot of stuff that is cool, and then it stops RX, and then it fails to start RX again. Failed to start RX again. Fails to. It works once. Why does it fail to start RX? You know what? There's a sample I can use. There's a sample I can use. Let's go look at the I2S sample. Drivers. Any questions while I do this? Any questions? Because drivers, I2S. Well, okay, let's see. We know it. We know one pass works, so we can always stop at that and call that the thing for today. And then we will fix that, and then we'll come back and I will explain what we're going to do with the. I will explain what we're going to do with the. So let's look at this. Yeah. I don't see them doing anything with the block. You see this? They reset each block somehow. I have a feeling it's this. I have a feeling it's that. I have a feeling it's that because that also follows the memory slabs documentation that we had here. Here. I have a feeling it's that. So let's see. Okay. Okay, memsolver lock. So let's go back to our thing and see if we can allocate. We freed it, and we're gonna use it. And before we use it here, let's see if we can do k mem slab lock. So do they call prepare transfer? Do they call prepare transfer after trigger or not? So they call prepare transfer. Trigger start. So they allocate before they start. But I don't know which memblock but memblock is sort of public. Ooh, we might need to do quite a bit of assume. basically you want us to do here. Ooh, I've discovered something I don't know. So K mem slab alloc will do, and mem slab and mem block, and what is it? Okay, mem slab alloc. Okay, mem slab alloc. Okay, no wait. Okay, no wait. Okay, I'll just use that for now, and then we'll see if that actually breaks anything. And then in here, do I need primitives for kmem slab? No, that comes with the kernel.h. Okay, cool. Let's just try and build this. Okay, let's do a small recap because it's now going into almost 2 hours of the stream and I have to go and do something else. But this is what we've done today. We've basically managed to pull in audio into our application, and we can now sense audio out. The thing we need to do is, the reason I'm trying to fix this logger so that it loops while doing that, so that every time we're actually commanded to do a sense, we go and do square of the audio signal, or rather of the audio packet. And then by doing that, a root mean squared is basically a square that accounts for both DC, which is background hum, and AC, which is the actual signal. So if you want to read more about this, there's this here, mean and standard, and this is from the book DSP, the Scientist and Engineer's Guide to Digital Signal Processing. I'll do this and I'll put it in the chat. It is in the notes already, and that should enable us to. So what I want to do is I want to fix so that we can do this over and over and over again, not just for one packet, and then that way we can test with a quiet sound, with a noisy sound, and all of those things. Let's run that. So let's package it first of all. Okay. Put our device in bootloader mode, and then let us push it into the device. It's gonna push, wait until 90%, and then we jump here and we start the thing 80, 70, 90. Yeah, let's come here and do that, and as it boots, let's see what we get. Yeah. So it failed to read, it failed to start, it failed to read, it failed to start. Okay, cool. So I need to stop here, and then I will remove this. This will at least work once, I know. Let's see if it will work once, and then we're stopping for that. So what we need to get is our reading to be stable so that we can read over and over a lot of times. And then once our reading is stable, each time we read, we can do some sort of little mathematics or statistics calculation of that group of samples. And then in that group of samples, we can determine whether some noise was made or some noise was not made. This is basically a home implementation of something like Hey Google. Well, this is the beginning of it, okay? This is the simplest mode of it. Just detect whether some threshold in sound was crossed and whether that threshold was not crossed. And basically it's called amplitude threshold detection. You set an amplitude, you set a threshold in your amplitude, and you check if your wave crosses that thing. Does anyone have any questions right now? Clearly, I'm going to commit this. Clearly, our code is broken. But it's broken in a good way. Git status, git diff dash dash staged. So this was what? Yeah, this was just a working. Okay, git commit. Wait, what did this do? Git commit dash m audio sense, add audio thread and set up I2S. Okay, git status, git add src, git diff dash dash staged, git diff dash dash staged. So this is what we did formatting. We did formatting and we started actually periodically recording audio. Git commit dash m audio sense, do formatting and start recording audio samples and format code. Okay, and then I will do git push, and then it's gonna be like, no, you must make a remote branch, and then I'm gonna do it, and then it's gonna work. Yeah, there he goes. Oh, okay, so there you go. We will go and open let's go and open a pull request in our branch here, custom DSP, and then it will go here. We will realize there is a new branch, compare and pull request, add audio sensing, attempting to add audio sensing capabilities to the app. Okay, amazing. So here we go. We are going to make a pull request and we're going to try and add audio sensing to that application. And we have established audio sensing collects samples once. However, it does not do it periodically, as we have a bug in our error management that causes it to fail the next periodic recording. Okay, comment, and then I want to go back to the build that has been finished here, and then let's package it. Cool, and then let's restart this. Let's put the application in bootloader mode, and then let's go push it onto the device. And then once we push it on the device, we finally look at the logs, and then we can stop there for today. That would be awesome. So yeah, let's look and see. Yeah. Okay, cool. So you see, exactly. Basically, this is what happens. We can put this in our thing. Here is the current log. Let's actually edit this a bit. Fails with the following log. complete comment. Cool. So we get that log when it fails. Okay, amazing. We've added audio. We know what we're going to do with this audio. Whenever we get this audio, we're going to go through it and calculate something called a root mean square. Root mean square. Root mean square. Yeah, so we're going to calculate a root mean square. And what is a root mean square? The root mean square, or RMS, is a set of values of a set of values, audio signal, is the square root of the set's mean square. So you get a mean and then you square it, which gives you a variance, basically a power of the signal. And then its RMS is denoted at X RMS or RMSX. RMS is also known as the quadratic mean. And what is the use of this thing? So yeah, so you see that. The RMS is in, I want to see it in signal processing. RMS is used in audio engineering to measure signal volume, particularly in the case of audio processing. The alternate measurement is peak volume. So do you see what we're doing? We want to measure the volume, the signal, how much, the volume of the signal. Okay, and then we can detect something like a clap, or we can detect something like a shout, or we can detect something like a falling or a glass breaking. Basically, right now we just want to measure the volume of the signal. And once we've measured the volume of the signal, we can extend it and start recognizing this signal slowly. Okay, but given that, this is a very nice introduction into audio DSP and DSP, digital signal processing in general, and audio processing in microcontroller land. And this is why you need statistics and linear algebra every time. Thank you so much for hanging out today. That was amazing. If any of you who's watching has any questions, I'm going to hang out for a couple of seconds or minutes, and we can answer some questions, and then we can go on from there. That was a lovely stream. Yeah, let's see. Any questions? Any more questions? Well, if no one has any questions, thank you so much for coming today. Thank you so much for hanging out with me, and I'll check you tomorrow when we extend our application. Amazing. So let's end this.